so much for inviting me today. I'm really honored to be here, and I'm very happy to get the opportunity to talk a bit more about p-hacking and especially the paper that we wrote and we published a few months ago. So my talk today is going to be called Gazing into the Abyss of P-hacking, and I think it is a relevant metaphor because we often hear don't p-hack or p-hacking is bad for science. It really feels like we're standing at the edge of this cliff, and it's like there's this cliff, don't fall down, don't do it, it's bad down there. But we rarely actually look down and see what's actually happening there. So we rarely actually really talk about what is p-hacking and what makes p-hacking different from other questionable research practices, and how bad is it really. So what happens if we do it? And this is what we intended to do in this paper that we published. It's called Big Little Lies, a compendium and simulation of p-hacking strategies, and this is basically what I'm going to talk about today. I published this with Felix Schönbrot from LMU Munich. He was my collaborator on the project and also the co-supervisor of my PhD thesis. And you can find the paper either under the official DOI or on SciArchive. Maybe you want to actually use the SciArchive version because the plots are prettier. Anyway, so let's start with this. So the first question is, what even is p-hacking? So what is it that we are trying to avoid? And when we went through the literature and we looked for definitions of p-hacking, we found out that it's actually very difficult to find a proper definition of p-hacking. So usually what happens is that papers define p-hacking by examples. So for example, like this paper from Simonson from 2014, which was very influential, that said a researcher may run a regression with and without outliers, with and without a covariate, with one and then another dependent variable, and then only report the significant analyses on the paper. So this is the definition they give of p-hacking, and what comes to mind here is that this definition is all based on mentioning different p-hacking strategies. So analyzing the data with and without outliers, with and without a covariate, and with one and then another dependent variable. All these are different strategies that are mentioned. And what is important here is that different papers mention different p-hacking strategies. And but the issue was nobody had actually ever really compiled these p-hacking strategies that were mentioned or looked into these p-hacking strategies in more detail. And so this is what we were trying to do with this paper. And so we compiled a list of these p-hacking strategies, and we try to simulate their impact on the false positive, the type 1 error rates in hypothesis testing. And we try to use these simulations to evaluate the effectiveness of potential countermeasures. So why did we even want to do this? So our motivation was that we wanted to, first of all, get a better understanding and a better definition of p-hacking. Since everybody seems to have like this slightly different definition that involves different strategies, we thought that it may be good to get a better overview of what even constitutes p-hacking and also what doesn't constitute p-hacking. Personally, I think it is very important as a scientific discipline to be clear about our definitions, about our wordings, and to discriminate between different terms. And I think this is something that is very important to also bring meta-science as a discipline forward, to just achieve this clarity of terms. Now, the second motivation was that we wanted to improve simulations of p-hacking. What we've seen in literature was that p-hacking, there's a lot of research on p-hacking, and there's a lot of simulation research on p-hacking, but these simulations often focus on one or two strategies maybe, and we just wanted to see whether we can like how to simulate other p-hacking strategies, and sort of also raise awareness for what may or may not be different. Our third motivation was that we thought, like, we've seen a lot of meta-scientific research on p-hacking. So for example, there are these surveys, I think very well-known papers, for example, the survey paper by John et al. That ask people about questionable research practices, about their use of p-hacking, to figure out how often people even use questionable research practices in practice. But our motivation was here to provide a bit more of a solid basis for this, like an idea of what other surveys, for example, could ask about. And of course, and this is also something we try to do with within the paper, but I think this is a way bigger project, and we just took a tiny step in this direction, is to get ideas for more effective countermeasures against p-hacking. So what can we do to actually avoid p-hacking, or to handle, to interpret literature that, where p-hacking has happened in the past. So how do we deal with this literature? How can we interpret it? What are potentially effective countermeasures that we can use both in interpretation and also in as a prevention for p-hacking? So to come to the first, talk about the first objective, which was getting a clear definition of p-hacking, it's of course important to discriminate p-hacking from other questionable research practices. And there are two questionable research practices that I want to talk about, which the first of which is HARKing. HARKing is a practice, it's an acronym, and it's an acronym for hypothesizing after the results are known. So essentially making your hypothesis fit the data. And at least from what we've seen in the literature, the difference in terms compared to p-hacking is that p-hacking is sort of making your data fit the hypothesis. So with one of these practices, you you adjust the data, and with the other you adjust the hypothesis. We also found the terms Procrustean and opportunistic for these practices. Procrustean comes from this old Greek, ancient Greek story of Procrustes, who was a bandit that would cut off the legs of his victims to make them fit a bed. So in the same way, you would like cut off some aspects of your data, some like data points, for example, to make them fit your hypothesis in p-hacking. Whereas with HARKing, it's more opportunistic. So you look at the data, you see what are the results, and then you say, I knew it all along. But of course, there are many boundary cases. So for example, what would you classify using multiple dependent variables as? You could either say it's p-hacking because you're adjusting the data, you're adjusting your dependent variable, or you could say it's HARKing because you're actually adjusting your hypothesis. And so this is just something we'd like to raise awareness for, that there are these sort of boundary cases. We tried and include as many of these boundary cases as possible. So if I'm talking about p-hacking later on, some of this, we can also discuss this afterwards. Some of this you may actually want to classify as HARKing. The other term that should be distinguished from p-hacking is publication bias. Publication bias is, I'm sure you all know this, suppressing non-significant results in the literature. And the interesting thing is p-hacking can also sometimes very much look like publication bias. And that is when someone is suppressing non-significant results within a study. For example, if I conduct many different hypothesis tests and I report only the significant ones, then this could also sometimes be interpreted as self-imposed publication bias. So again, we have these borderline cases here. For example, also if people conduct more than one study and then only report the significant study, is it still p-hacking? Is it publication bias? Here we were trying to be a bit stricter and just include like everything that we include for as p-hacking strategies are strategies that you would be able to apply with only one data set. Now I've talked a lot about these strategies and so here you see a full overview of the strategies that we found mentioned in the literature. I should say that these are probably not exhaustive. Actually, there may be many other p-hacking strategies out there, but these ones were the ones that we found mentioned more often, or strategies that can be applied to a variety of different data sets or research questions. So there's selective reporting of the dependent and independent variable. There's optional stopping. Outlier exclusion is when you selectively define which values are outlier or not, and then exclude these and these outliers. Controlling for covariates means including different variables as covariates in regression analyses, and then seeing whether the regression will come out significant. We have scale redefinition. This is a strategy that we found mentioned that is directed at like psychological scales. So, for example, and a questionnaire and inventory where different items can be included or not included based on significance. Then variable transformation means transforming your dependent and or independent variables in different ways. Could be log transformation, could be like taking the inverse, taking the square root, whatever. This is in different fields. This is more or less common, and that different transformations are more or less common. But statistical significance can also depend on these transformations that were performed on the data. Discretizing variables. What we mean with this is to form categories out of an underlying continuous variable. So this is often brought up in, for example, research that includes age as a variable, and then you have all these different age categories, and you may have like young people and old people, and then you set the cutoffs at different different values. Exploiting alternative hypothesis tests means taking a different an alternative hypothesis test. So, for example, a non-parametric or a parametric test that tests the same underlying hypothesis. Again, here, this is more common in some fields than in others. And I think this strategy is particularly relevant in fields where models are quite complex, and you have a lot of different options of how to formulate the models that are at least, at first glance, very similar, and it's just ambiguous which one's the right model. Favorable imputation relates to imputing missing values. Of course, this would only be possible if there are missing values in the data set. Trying out different imputation methods to find a significant result. Subgroup analyses means dividing, including or not including certain subgroups. For example, running the same test once in the general sample, and then only for men, and then only for women. And incorrect rounding. The last one is rounding down your p-value, so that, for example, if you get a p-value of 0.051, you round it down to 0.05 so that it's significant. So this is a quick overview of the p-hacking strategies that we were talking about. Again, probably this is not an exhaustive list, but we still think it is. It gives a clearer picture of what p-hacking can look like. Now, the next step that we did was to simulate p-hacking. So we used a Monte Carlo simulation. That means we generated a lot of data sets under certain assumptions. For example, let's take the first example here. This is selective reporting of the dependent variable. And there we assume that people would test 3 or 5 or 10, conduct the same test with 3, 5, or 10 dependent variables. And these dependent variables may be not correlated at all, slightly correlated at 0.3, or extremely high correlated, for example, if they're measuring the same construct or the same, like similar questionnaires, having an extremely high correlation at 0.8. And so we simulated these data a lot of times. In our paper, it's 10,000 times, and each time simulated this p-hacking procedure. So basically conducting here's a t-test with 3 or 5 or 10 dependent variables, and then seeing what is the false positive rate that we get if we do this. So this is the probability of having at least one false positive result. I should also say that we always simulate it under the null hypothesis. So in all these cases, whenever there's a significant result, it's a false positive result. So we did this for all the different strategies under different environments, different conditions, to just see how bad is it. And it was clear to us from the start, actually, that it would be bad. I mean, there's a good reason for why everybody keeps warning about p-hacking, but there were some strategies that we were actually also quite surprised at how bad it really is. For example, at least for me, one of these was variable transformation, where we assumed that researchers would use 3 or 4 very simple transformations on either the x, or like the predictor, the outcome variable, or the predictor and outcome variable in a regression. And you can see that if you do this, you get quite high false positive rates of like 30% or more. And especially in fields where this is very typical to do, like this is not something people would necessarily expect like this. In the same way, for example, scale redefinition. A lot of people, when they learn how to use psychological scales, they look at Cronbach's alpha. And if this reliability, the scale reliability indicator is not high enough, they throw out items that make this Cronbach's alpha coefficient go down. So, and this is basically what we simulated here. Just so if the result was not significant, the item that was worst for the reliability of the scale would just be thrown out. And then the test would be conducted with the rest of the scale, and the item that would be thrown out because it wouldn't belong to the scale. So, and these are the results that we found, and you can see that with a big scale, we can like the false positive rates can go very high. So this is sort of the central overview graphic of the figure that provides an overview of all the simulations, of all the different p-hacking strategies that we did. And so what you can see is a lot of dots, but I think what becomes clear from this figure is that the false positive rate in each of these strategies can become very high if we have the right environment and if people do it just aggressively enough. What does aggressively enough mean? It means conducting many tests until a significant result has been reached. So if people are willing to conduct a lot of tests, they are quite likely to obtain a significant result, no matter which single strategy they use. And I think this is an important takeaway, because we often try and limit we try and limit p-hacking, and but what this shows is that if we don't consider all the strategies, then we may miss out on one strategy that will then be used intentionally or unintentionally. We're not assuming that anyone is the bad guy here. But if people intentionally or unintentionally use just a single one of these strategies, they may already obtain very high false positive rates. Now, if you don't agree with any of the simulations that we did in the paper, I mean, you can take a closer look at those. But in general, if you have a very specific question of what you want to do, we've got this Shiny app that you can use to simulate p-hacking in the same way that we did, with whatever parameters you want. So then if you have a specific question of how bad is this specific p-hacking strategy, you can just go to the app, do the simulation, download the data set, and then also perform whatever analyses you want to perform on the p-hacked for the p-hacked p-values, for example. We hope that this may also, for example, be used for simulations in the future, so that just future research can build on this, and so that not everybody needs to write the same code over and over again. The question is, of course, in practice, people rarely apply just one p-hacking strategy, but they probably apply more p-hacking strategies, one after another. So, for example, if my first test that I conducted wasn't significant, I'll conduct a second test with a different, for example, statistical analysis. Then I'll use a different dependent variable. Then I'll throw in a covariate into the model, etc. So you end up with, in practice, these combined strategies that have a whole procedure of applying different p-hacking strategies. And so what you can see here is that, of course, if you apply more than one strategy, the probability of obtaining a false positive result will increase. But it's not exactly additive. So depending on the data set, depending on the strategies, the additional increase in false positive rates will not be exactly what you get if you just apply this one strategy. This is just the case because there will be some results that are almost almost significant, and it basically doesn't matter which strategy you use. There are lots of strategies that will push these results towards significance. So the take home of this of our simulations was that the severity of p-hacking depends on both the p-hacking aggressiveness, so how many tests you are willing to conduct, and on the data environment. We can also see that strategies mentioned less often in literature, for example, variable transformation, can have very strong effects. We can also see that every single strategy, if used aggressively enough, can yield very high false positive rates. And if you use multiple p-hacking strategies one after another, then this has a slightly less than additive effect. An additional distinction that we noticed while writing the paper would be is very useful to make is between p-hacking and reporting strategies. And the false positive rate in a p-hacking strategy depends only on how many tests you are willing to conduct. But still, a lot of papers about p-hacking mention they distinguish between different p-hacking strategies as, for example, reporting the first p-value that was significant or the smallest p-value that was significant. But what we found out sort of while writing the paper is that it actually makes sense to view these reporting strategies as something else, something different from p-hacking, because these reporting strategies will not influence the type 1 error rate, which, of course, logically it makes sense. It's just not immediately obvious, I think, from the literature. So if you want to talk about how bad is p-hacking, it makes sense to look at just the p-hacking strategies. If you are interested in what does it do with the p-value distribution, for example, it is important to also consider the reporting strategy. So, for example, whether someone reports the first significant p-value or the smallest p-value. As you can see up here on the right, this matters for the p-curves, but it does not matter for the false positive rate. Now, finally, what we also did was we tried to give some preliminary ideas about how we could evaluate solutions to p-hacking. What we can do about p-hacking and what may help and what may not help. So what you could see before was that in the simulations was that we simulated all these p-hacking strategies with different sample sizes, and there's this idea that larger sample sizes help against questionable research practices. But in the case of p-hacking, as can be seen from our simulations, larger sample sizes alone usually don't work. They're good for a lot of things. Larger sample sizes give greater power, etc., lower false discovery rates. That's all very good, but it doesn't help against p-hacking. Only because the sample size is big, p-hacking strategies still work. Then there's this idea to redefine statistical significance, the Benjamin paper from like 2017, I think, that we should decrease our significance level to 0.005. So we try to repeat our simulations under with this decreased alpha level. And what you can see here is that the dotted line would be a 10-fold decrease that we would expect in the alpha error rate. But the green line is what actually happens. So if you apply the same p-hacking strategies and the same severity, you don't just you can still get results that are your false positive rates are still way above 0.05 if you do this. So while redefining statistical significance lowers the overall false positive rate, it does not decrease as much as you may expect. Some people also suggest to report effect size measures, and I think this is generally a very good idea because it gives you something more to think about, some other statistic that can sort of describe the results. But what you can also see is that if these p-hacking strategies are applied, then at least in the cases where it works, the effect sizes that get reported will also be inflated. So if a result that we see in the literature has been p-hacked, the reported effect size will also be an overestimate of the actual effect size, which was in this case here always 0. Another idea is to sort of abandon frequentist hypothesis testing and to report Bayes factors instead. Here it's kind of similar to effect sizes in one sense, where what you can see is here, like the orange results here are always the p-hacked results, is that of course if we apply p-hacking and then report a Bayes factor with the p-hacked p-value, the Bayes factor will still be it will be biased towards the alternative. So here Bayes factors larger than 1 show evidence for the alternative. Bayes factors smaller than 1 show evidence in favor of the null hypothesis. What you can see is that there's this second sort of elevation in the curve for the p-hacked results, where Bayes factors that are too optimistic in favor of the alternative are reported. But what we can also see is that at least if the sample size is also increased, Bayes factors for p-hacked results may actually mostly show evidence in favor of the null hypothesis. So here we would see conflicting results for the frequentist and the Bayesian hypothesis test, which we think may at least make people think twice about the results. Now, another idea that has been brought up is to correct for p-hacking through some, like same as with publication bias correction methods. Essentially, look at the literature, assume some way of how p-hacking took place, and then correct for the occurrence of p-hacking in meta-analytic evaluations, for example. And so personally, I find this very difficult, and I'm not sure if this can be really achieved in a way such that we don't have over or under correction, just because if you look at the literature, there will be so many different ways in which people will be will be p-hacking. There are so many different constellations of dependent and independent variables and correlation structures in the data sets that there are a lot of assumptions that you would have to make about the single data set, or very strict assumptions about all data sets being the same within an area of research. So it's, to me at least, it seems very unlikely that we will ever find a way that is a good way to correct for p-hacking. Now, the last option is pre-registration or register reports. So does pre-registration help against p-hacking? And I think what our results, our simulation results show very well is that pre-registration can help, but only if it fixes everything. So as soon as p-hacking is still possible, with one of these, even just one of these strategies, if this strategy is used for p-hacking, it can still lead to very strongly inflated error rates. So pre-registration is useful for a lot of reasons, but at least if someone intends to p-hack, it can only be a good countermeasure if it's really fixed and if it really fixes basically everything. Now, I'm happy to talk about whether that is sensible or not, because we also say we don't want pre-registration to be a prison, etc. Everybody has heard this term. So I'm not sure if we should even do this, but our results kind of show that we would have to do this if we want to claim that our pre-registration actually has some influence on the ability of researchers to p-hack in the study. So to summarize, what we tried to do in this project was we compiled a list of p-hacking strategies, because we noticed that many p-hacking strategies are mentioned very rarely in the literature, others are mentioned very often, and we think that the p-hacking strategies that are mentioned very rarely have a danger of falling through the cracks, and that people suddenly think that this is okay. And our simulations show that it's not okay. So if these p-hacking strategies are applied, they have a strong impact on false positive error rates. In fact, if applied aggressively enough, all p-hacking strategies can have a substantive effect on false positive rates. We also try to provide a preliminary evaluation of countermeasures, and at least I was very disappointed, frustrated at the end, because eventually, at least my conclusion was that what probably is the best course forward is if we just educate people about p-hacking to try and prevent it from happening, because correcting afterwards or finding out whether someone p-hacked is going to be very, very difficult. So yeah, I hope this gave you a good idea about our project, and I'm happy for any questions and discussions.
Thank you very much, Angelika. Hi, everyone. You can leave your questions in the chat or just raise your hand. Meanwhile, I'll go ahead with my quite naive question. So first of all, thanks very much for sharing all the strategies and including educating and surely your session, your talk is going to contribute towards this general educational theme on p-hacking. I can't help thinking about though that the countermeasures, they're more targeted at the individual level, and I would be interested in knowing what you think, because there must be reasons why people have to resort to p-hacking strategies, and probably many of us, these p-hacking strategies that you have just discussed, they can resonate with quite a few of us. So yeah, and I'm thinking, so how could this be addressed at the more systemic level? It would be interesting to know what you think about this.
Yeah, thanks. That's a very interesting question. I think first of all, it's always very difficult to propose something about changing the systemic level, just because it just, at least for me as a junior researcher, it just feels so fixed. So I think there's a general problem in the incentive structure that, I mean, we're still in a phase where significant results are just more likely to be published. So at a systemic level, I think probably practices like registered reports where results are published independent of significance will really help making p-hacking with the goal of obtaining significant results less attractive. I think other than that, I think, yeah, I already mentioned education, of course. Like I think especially with a lot of these strategies that I mentioned, a lot of people are just not aware that they're p-hacking, and even though we've talked about p-hacking for like 10 years now, I think, for example, scale development, like throwing out items out of scales and then retesting with a different scale or something, it's just something people don't even notice they're sort of doing and influencing their significance testing results by doing so. So I think there's just there is like some education is still, at least in my view, necessary, and I think yeah, that institutions like you, for example, yeah, reproducibility networks that organize workshops, etc., like could really help with this. Yeah, institutionally, I'm not sure. I think I sometimes also wonder to what extent we can avoid it, because it's like it's a type of bias, and there's a lot of hindsight bias at work in science, for example. And I think if I see the data and I see a certain pattern, then I think it's kind of natural, like a human quality, to sometimes think, oh yeah, I thought, like I figured this out before. Yeah, I thought this would happen. So I think maybe it's also it comes in with a broader directive to kind of counter also other biases in science. And I hope we can work on this, but yeah.
Yeah, thank you. Thanks. It may sound not very optimistic, but I do appreciate having honest conversations about that. I think it could be a good start in itself. So we are having a question in the chat from Deepsiha. So hi, Angelika, love the talk. You talked about correcting for p-hacking as a solution. What are some methods to do that? Are there statistical corrections applied after analysis or something? Sorry, there's few questions. So how effective are they? I'm just curious about this. I can repeat the questions if you didn't remember all of them.
No, it's a good. I can also read them actually in the chat. Yeah, I think yeah. So there are definitely methods for correcting p-values. There are also tests for whether p-hacking happened in the literature. So like they're quite similar to publication bias correction methods in that sense, and they all make very strong assumptions. So essentially what they do is to look at the p-value distribution and then test whether this p-value distribution could occur naturally, basically. But what naturally means is underlying very strong assumptions. So, for example, if you have to assume that all, like the strictest test would be like assuming that all of the results were null results. And actually, there's no effect in none of the studies. So, and of course, that doesn't make much sense. And these methods are, of course, more sophisticated. But they are based on assuming something about the effect sizes in the population, and then deducting from that what the p-value distribution should look like, and then seeing how much does my p-value distribution differ from this. Or, for example, is it what's the shape? Does it have a slope on the left or the right, or for something like this? And of course, all of these methods, if you read the papers, they claim that they're effective, and they usually prove this with simulations. But then, at least the issue that I see is that they're tested in environments where that sort of favor the method, because these environments are based on the assumptions that the method makes. So in these environments, of course, if the assumptions are true, then the methods work very well. If the assumptions are not true, and we just don't know if they're true or not, because we don't have like in the literature, we don't know how much p-hacking happened, whether p-hacking happened, what types of p-hacking happened. We don't have a ground truth. So we kind of don't exactly know how well they would work in practice. And that's the big issue that I see with these methods.
Thank you. There is another question in the chat from Philip. Do you think that if it became a cultural norm for researchers generating data to pass the analysis to an independent trained statistician, this would improve things?
Oh, good question. I think it's difficult, because I think often researchers are have the most expertise on their own research area. So often involving an independent statistician may while I think involving an independent trained statistician would avoid some problems. For example, they could tell them about multiple testing, etc. And maybe they would be more bias-free in that sense, because they're not as personally involved in the research goals. So I think it could get rid of some of the biases. That's also why, like, for example, blinding analysis data, etc., may have benefits. But at the same time, like independent trained statisticians may lack the substantive expertise in the research area to, for example, actually evaluate whether some outcomes make sense or not. So I've discussed the definition of outliers, for example. Now, of course, I can tell a statistician what values a scale can take, but they may not be qualified really to assess whether it's normal that someone would max out the scale or not. So I think there are lots of aspects in data analysis where the expertise of the research groups actually comes in and is also very helpful. And I think in the whole p-hacking discussion, we sometimes don't really appreciate this expertise enough as well.
Any more questions, everyone? Just to remind again that I'm recording the session. I will be sharing on YouTube and then sharing the link on our Twitter account. Please do follow us for more updates. Meanwhile, thanks everyone for coming along. Thank you very much, Angelika. Very interesting, very topical, and useful as well.